Hey everyone, welcome to this DP900 V2 study cram. So I did a version a couple of years ago and I felt it was time to update it. As always, if this is useful, a like and subscribe is appreciated. Now the DP900 is one of those fundamental certifications. If we quickly jump over, here we can see we have the basic information about, hey, yep, this is the Azure Data Fundamentals certification. This is very broad. You don't need to know super detail about any particular thing. But if we go and look through this page, what it's going to show us is, well, hey, there's the study guide. So the study guide is going to give you the key information to help you prepare for the exam. What are the core skills that I want to be able to tick off and say, yes, I know this. So if we scroll through, it's going to say, hey, look, the overall skills measured, the functional groups, and the exact skills. So I want to be able to go through this entire list and say, yep, I know these. Then it's also got some sample questions. So it's nice to go through those, give you an idea of the type of things I should be able to answer. And then, so I'm familiar and not panicking about the environment, there's an exam sandbox, just so I can get used to the graphical interface, the styles of questions that I might see. If I keep going down in the document, it's then going to have, hey, how I can actually go and schedule the exam, but also free online training. And I would definitely recommend you go through this to get a good idea and help learn the information to help and make sure you are actually successful. My goal of this study cram is really in hopefully an hour or two to just refresh some of those core concepts, maybe watch it just before you take the exam to increase your chance of being successful. Again, I don't need to know super deep the information. It's a 60-minute exam. Number of questions may vary. I think I had about 45 when I did it. Finished very quickly. There's not case studies, there's not labs. It's very much multiple choice. Hey, what do I want to use for this particular thing? Don't stress out. If you don't know an answer, eliminate the obviously wrong ones and then take an educated guess. Azure isn't trying to trick you. So what seems most logical based on what you do know, and have a best attempt at it. At the end of the day, if you don't pass the first time, it'll show you where you was weakest. You'll go back and you'll get it the next time. So with this, let's jump into it. Now, when we think about Azure services, one of the things I want to quickly review is when I think about interacting with Azure, I, as a human being, I'm sitting here at my machine, and there's different ways to interact with Azure. I can use the portal. The portal is very good for, it's intuitive. I can start to learn about what's available to me. I might go and do some investigations. I shouldn't really be creating things in a production environment. I want to be using templates. There's things like PowerShell, the CLI. These are great for doing automations, creating scripts to do things. And then yes, we have things like templates. Templates have the benefit that they are declarative. I state what is my desired end state, and it makes it so. I don't have to tell it how to do something. I just say what I actually want to happen. There's many types of templates. There's things like the Azure Resource Manager JSON. You'll hear things like Bicep. And then there's things like Terraform. This is a third party, but again, a declarative technology. But these are all files that state what do I want the end state to be. And the benefit of these, I can put them into Git repos, for example, like GitHub or Azure DevOps repos. I can use pipelines to deploy them. I can do change control on them. So we really want to focus on this. But no matter what I do, when I interact, when I want to actually interact with that cloud service that is Azure, everything actually goes through something called the Azure Resource Manager. That is the RESTful API through which I talk when I want to do things into Azure. And when I think about Azure and that Azure Resource Manager, there's really two levels to our interactions with many different things. I can think, for example, there's an idea of a control plane. So a control plane is when I'm interacting with the Azure resource itself. So I can think about management. I want to create a resource, delete a resource, maybe modify a resource. And then completely separately, what we have is then a data plane. If it's a blob, if it's a storage account, if it's a data in a table in a database, we have a data plane. And the really important thing here is at the control plane, we have things like resource-based access control. That's at the resource level. And that gives me permissions to perform things on the resource. However, that does not mean that gives me permission at the data plane. Just because I have access to the resource doesn't mean I have access to the data. So the data plane, now, some of them do support now role-based access control data. So it could be there is a data plane role-based access control. It might have its own key or shared access signature. It might have its own ACLs, access control list, ways to define who can do what. But the key point about this is realize that just because I have some permission at the control plane does not mean I have permission at the data plane. And we can see this very quickly. So if here I jump over quickly to the portal, if I was to look at something simple like a storage account, and I can pick any storage account I want, if I look at the access control, what we can see is there are many roles available. Now, most of these are focused on their ARM control plane. If I look, there's actions, and these are actions against the resource provider, but at the control plane. But none of these would actually give me permission on the data in the storage account itself. I could not interact with a blob or a queue or a table. But storage accounts are one of the services that do have data plane RBAC. So if I look at a data role, like blob data contributor, blob data owner, blob data reader. There are also ones for queue and for table. If I look at one of these, this one doesn't happen to have control plane, but it has data actions. So here I can see I can set data control plane. Is if you see questions about, hey, you have this control plane role, what data does this let you see? Typically, it's not. I need something at the data plane to be able to actually interact with that data. So that's really the important key part of that. Now, when we think of types of service that we can have in Azure, there's this whole idea of there's different layers in Azure and there's different responsibilities. So I can absolutely think about, for example, there's obviously hardware. There's the physical fabric, storage, compute clusters, networking. Then there's a hypervisor. This is based on Hyper-V in Azure. And all of the different services then build on top of that. Now, what you also then get is things like an operating system, a runtime, a middleware, maybe an application that actually provides business value, and then data. And so our different types of service will do different things for you. You have different responsibilities. So one of the things we always think about is, well, infrastructure as a service. So if I'm infrastructure as a service, well, you're responsible for this stuff. Picking the OS, managing the OS. So things like backup and patching. And hey, I go and install a database inside that IaaS VM. I'm then responsible for installing the database application. I'm responsible for tuning it. I'm responsible for minor updates, for major updates, for upgrades. I'm doing all of those things. Whereas if I think about things like a PaaS offering, platform as a service, the line of responsibility now becomes, I really only care about writing my app and worrying about my data. Azure is now taking care of these parts. I don't see an operating system or a runtime or middleware. It's done for me. Now, both of these will apply when we think about data services in Azure. We have a choice. For example, as I mentioned, I could absolutely install a database in an IaaS virtual machine. So with my database product, hey, I've got my database that I want to install. And that database, I just do an installation. But then I'm thinking about things like, well, when do I back it up? Updates, tuning, maintenance, all of those things are my responsibility, both for the operating system and the database itself. As opposed to, in this world, we have this database as a service where the database is managed by Azure. It's just installed by Azure. And there's many examples of this. There are things like the Azure SQL database, Azure SQL managed instance. There's all the managed databases like Postgres, MySQL, MariaDB, etc. That's the wrong way around. There's things like Cosmos DB. So the key point of these is when I use those PaaS databases, those databases as a service, I'm not worrying about an operating system. I'm not worrying about patching the database or the minutiae around the backup. There might even be auto-tune. There might be other services built on top of that, security built on top of that. Those are really just done for me. And so when I think about the benefits of these kind of scenarios, when I have these database as a service, we really do think about things like, well, they're evergreen. By evergreen, they're constantly getting new functionality. They're constantly getting those updates. It's just performed for us. I'm going to have features like auto backup. And maybe there's some configurations I can do about retention. Maybe I can manually add in extra backups, but they're just going to be done for me. They're often going to have things like native high availability. And maybe I have options to add read asynchronous replicas to other regions, for example. So it's going to vary by service, but those are the basic ideas behind them. They might have things like auto scale. I have a lot of flexibility in the scalability of those solutions. I have less management to do. And that's really a key point. When we move from this world of IaaS to PaaS, it's about a shift of responsibility. In that IaaS world, I'm responsible really for everything. There are things to help me, but it's my responsibility. As soon as I start to use the database offerings in Azure, I'm responsible for a lot less. A lot of it is done for me, and I can really focus on the key, maybe design elements of the database and using it for my application. Now, a key point when I have these sorts of solutions, for the most part, there is no OS access. It's doing those things for me. Some of them might let me stop and start, for example, the compute things to optimize money. So these different types of service. And most of what we'll talk about in here are these database as a service offerings. Again, you can install them into an IaaS VM. There are even some features added if I have things like SQL Server installed on an IaaS VM. But most of the time, our goal when we use the cloud is I only want to be responsible for the things that help me differentiate and give me business value. I don't want to be managing an OS if I don't need to. So as much as possible, we try and move up through the layers. So, hey, I'd rather be using a database as a service and just not care about patching an operating system or worrying about securing the operating system. Now, whether it's an IaaS or a PaaS database, realize I still need to be able to access it in some manner. So once again, I can think about, well, okay, I'm sitting on a certain machine, and that machine is on a certain network. Great. And then what I'm trying to get to is that database. So there's some database service. Now, whether that database service is a PaaS offering, or it happens to maybe be running in some IaaS virtual machine, whatever that is, there's a set of processes that offer me access to that database that go and connect to some storage. Maybe I can't see that storage, especially with the database as a service offerings, but I want to be able to get to it. So how do I do that? So a step one is I have to be able to find it. It's going to have a name, a DNS name. So firstly, there's an idea of a DNS resolution. So I have to be able to resolve the name to an IP address. And we want the name because often when we talk to these things, it's going to be encrypted. TLS communications, which means the certificate has the name of the database, not the IP. So I have to be able to connect to it using the name of the database. So if I'm not, for example, on a virtual network, if it's tied into a virtual network in some way, if I'm on a remote network, hey, I still have to have DNS resolution to it. And often these have a public endpoint. So it's some IP address that's accessible via the internet. So once I resolve the IP address, well, then I have to be able to get to it. I have to have a network path to talk to that IP address, which means if there's firewall configurations, for example, I have to make sure the IP address that I'm coming from, maybe it's my direct IP, or more likely there's some network address translation on my network which is visible. I have to enable that connectivity. But also, we may use things like an Azure Virtual Network. So an Azure Virtual Network is a set of IP ranges. It's a construct that lives within a subscription in a certain region. Maybe we don't like this public endpoint. I don't want this public endpoint that anyone could connect to. So instead, we have this capability to create something called a private endpoint that points to a specific instance of a database service. So if I'm sitting on this VNet or anything connected to the VNet, I can then talk via this address, and I could essentially block off this public endpoint if I wanted to. Now, if I'm sitting on a remote network, obviously I have to have a network connectivity to get to that virtual network. So that could be something like a site-to-site VPN between my maybe office location and that virtual network. It could be a point-to-site if it's just at home. It could be something like ExpressRoute, private peering. But there has to be a network path to get to the VNet that has that private endpoint. And then, of course, once all of that is done, I still need permission. Just because I can get to it doesn't mean I'm allowed to interact with it. So I have to be able to resolve the name. I have to have a path to either the public endpoint or a private endpoint if I've enabled that. Then I have to have some way to authenticate and be authorized. Authenticate is proving, hey, I am who I say I am. Authorization is, well, I am who I say I am. What am I allowed to do? So I have to have some method to get permissions. And again, maybe that's integrating with Azure AD. Maybe it's using some shared access signature. Maybe it's a key. There's many other different things I can do. But I have to have that in place to use any of the data services. So there's no magic involved in this. I have to be able to resolve it, get to it, and then have permission to it. So that's just kind of the bare fundamentals we have to understand for the interactions. So whether that's an IaaS VM with a database installed or just a database as a service, I have to be able to do those things. Okay, so that's some of the basics around Azure. But then what do I do? What do we actually have? What are the types of data that I may actually want to interact with? And so we have this thing. We have this idea of data. And it would be nice to think of it as just, oh, there's just this one type of data. And what is data? I can think of data as a collection of information, a collection of facts. Now that could be numbers, it could be log entries, it could be descriptions, it could be observations around things. Those facts may follow a very, very strict structure. For example, if a fact is a date has a very fixed structure. If it's an address, that has a fairly fixed structure, but even that may vary based on country. Hey, some of them have a postcode, some have a zip code, some have a state, some don't have a state, some have a county. So there might be some flexibility. Sometimes there's semi-structured. There's certain attributes that are common, but they might be used in different ways. Some people have one email address, some people have 10 email addresses, some people have additional certifications or qualifications. So I need some flexibility in how I store the data. If I'm a grocery store, hey, an orange has a very different set of attributes to a box of cereal. So there might be very flexible structures. It might be self-describing. And sometimes there's no structure. It's an image, it's a media file, it's a Word document. So we have these different types of data, and based on the type of data, we're going to want a different type of service to actually manage it. So let's start off with structured. This will be the most, I guess, familiar when we think about databases. So I can think about structured. So that's one of the types of data. And even within structured, there's some flexibility around it. But the idea of structured is there's some kind of fixed schema. I'm defining, hey, there's entities. There's different types of entity. A person, an office, items for sale. And then there's different attributes those entities have. So as a human being, I have certain attributes, maybe a first name, a last name, a date of birth, an address, a phone number. As a building, maybe there's a GPS coordinate, whatever it is, but there's different attributes for the different types of entity. So we have a schema, which is the definition of what are the attributes for each of the types of entity we may have. So we have a very formatted fixed schema for each of the types. So if I have a well-defined structure of my data, then I can normalize. So normalize means, hey, I'm going to maybe split my data into those different tables, reorganize it, so I remove wasted space. I'm not duplicating things. It helps me ensure my data integrity. It makes it usable through standard types of interactions. So if I think about structured for a second, there are different ways I can think about this, but we'll start with this idea of a relational database. So I'm going to have a few different things here. So my whole point here is it has that schema. I have the well-defined attributes of the different types of entities. I'm going to normalize my data. I don't want to have this mass duplication. For example, I might have the idea of my company, and I have the people who work at a certain office. For every person, I don't want to list the office address. It would make far more sense to split out people and offices and then just reference the office in the separate table that the people work in. So I'm not duplicating data. So it's more efficient in the storage. It's going to be easier to interact with, and I'm going to have that better data integrity as I have that strict type of requirement for the different types of data. Now, when I have a relational database, I'm organizing it. I'm going to have tables. So I think about the idea that we create a table. And a table has a specific schema. So what we have in the idea of a table is we have columns. So I can really think a column is a particular attribute of this entity. And then within the table, we have multiple rows or records, individual entities of this particular type. So this is really the key point when I think about this. The schema defines what are those columns, what are the attributes. Each type of entity would have its own table. And this gives me a standard way to interact. The column, hey, they're the properties, the rows are the entities. So I might have a first name column, a last name column, a date of birth column, office ID I work in, which would then respond to another one. Now, when I think about this table and I have these entities, if I think about Office ID for a second, well, I want to have some ID that I reference. So very often what we'll have is one of these columns will be the key. So maybe there's an employee ID. So the first column might be employee ID, first name, last name, date of birth. So then maybe there's another column with job history. And it would have the job done linking to the employee ID. So I'm not duplicating the employee information. I'm normalizing it. I'm only storing the pertinent information and then referencing other tables where that's more useful. That's really the core part. And if I think about a typical relational database and I have these rows, think of it as that's the way we actually store it on the disk. So I can really think, okay, I'm going to store it as, hey, employee ID. So ID 01, and maybe it's first name Clark, last name Kent, and then date of birth, etc., etc. So this is how we are storing as rows, storing it that way. And so there's many, many other rows, but this is how it's stored on the disk. So when we interact with it, really the most useful way to interact is we care about the entities. We want to interact with the entities like this. Now there's another type. I can also think about columnar. So columnar, people say it different ways. But it might look the same. It might look the same as, well, there's rows and there's columns, but it is stored as columns. So on that underlying storage, it's actually storing, hey, Clark, Bruce, Diana. And then, oh, okay, the next one is, hey, Kent, Wayne. You get the idea. So like a Parquet file works this way. It stores it as columns. And why I might want this is how am I interacting with it? If most of my interactions were really caring about maybe summarizing particular attributes, well, this is really useful then because I can just load up, really read in the column and sum it or average it if these were sales numbers. So there are benefits on how I intend to interact with this. So that's really the goal of this. If I want to report on and act on really columns is what I care about, then storing it this way may actually be more useful to me. So that's why we have these different types available to us. So that's the traditional, very structured, and we're kind of used to that idea in databases. Now there's also, I could think about, let's use a different color. I could think about semi-structured. So if semi-structured, there's either loose or no schema. It might be considered self-describing. This could be a JSON file. That's a very common example of this. It could be an XML file. But it could even be something like really a CSV, a tab separated file, something delimited by a certain character. It can really be any format where there's flexibility, it self-describes within it. So I can think about, we call these commonly a document. And a key attribute is in some way it's self-describing. Now it will very commonly still have a key. There is some key that we have still to be able to identify records. I always want that. Now that key may also be used as something called a partition key. Or I might have a separate. If you think about, I have to store stuff. As we get bigger and bigger, I can't just store stuff as one big file. I might have to separate it into fragments. We call them shards. So I want to be able to shard my data. I want to be able to distribute the data, maybe over different files, maybe over different database servers, and they each host a portion of the complete database. So I want to know, well, how do I know when to shard it and which shard does the data go into? So partition key, that helps me do that distribution. So partition key helps me have an even distribution, and that even distribution is key. I wouldn't want to pick a partition key that was uneven. I don't want 90% of my data going into one partition and the other 4 have 3% and 2%. I get terrible performance. So it's really important we pick a partition key that's going to give us a very good distribution of our data. Sometimes we have to create a synthetic partition key. I can't just base it on some raw value. I have to maybe do a combination or do other things to get something that's really good. So I get this even distribution that's used to shard, separate out, distribute the data. And that sharding will go over logical partitions. So it's going to split into different logical groupings of data that then fundamentally will separate over physical partitions, i.e. different files, i.e. different database servers. But the key part here is there is no fixed schema to it. If we quickly go and look at a file for a second. Here I can see, hey, this is people. So I have a particular instance of a person. So they're in the curly braces. And in this instance, it is Bruce Wayne. But I can see it self-describing. It's telling me the attribute. It has powers. It has 1 power, money. But then a different person, Clark Kent, has actually a different attribute. It also has pets. And its array of powers, well, it has different. It has lots of power. Superman has everything. But it has different data available to me. There's no fixed schema. It can really just include anything I want. And here I'm using those square brackets to indicate an array. So I can have multiple attributes for that one particularly type of attribute. So what this is doing. And we're going to come back to these. But just think, hey, fixed, very defined schema. Hey, structured, relational database. Semi-structured, JSON, an XML file. Could be a CSV, a tab separated file. Could be a space separated. There's different formats for that. Then we have the idea of unstructured. There's nothing structured around this at all. We'll go with orange for this one. So I can break it off now and say unstructured. It's just bits on a disk. Yes, it's a file that could be a document. It could be a picture. It could be a video. It could be a blob, a binary large object. And there's different services around this. But very commonly what we're going to think about in an Azure world here, I would think of blob. So we have these binary large objects. And there are different types, but I could think about, hey, within there, I can store anything. I might store images. I might store video. I might store like a .doc file. I could store XLS, spreadsheets, PDFs, you name it. I can store anything I want in there. That's really the point of that. Now, there are other types of data. There's types of data where, for example, it describes relationships between things. So, for example, I could think about a graph. So graph is all about the idea that I have relationships I want to be able to express. Think about social media. Think about Facebook. So-and-so is a friend with so-and-so. So-and-so follows this. Think about, again, the people idea. So I could have the idea of, okay, we have these different types of nodes. So we have nodes, which are entities. So a node could be of type person. So this is John. And there might be another person. It's another node, could be Julie. There could be another node, but this time it's an office. And that could be Dallas. And so there's then the idea of relationships or an edge. So I could think of, well, John says a relationship. This is an edge. It's the type works at. Or this edge works for. Julie also works at. So it's very good for actually going and working out what are the relationships between the different types of entity I have in my environment. Now there are others as well. I have things like, let's do a different color. I'll run out of colors pretty quickly here. Oh, I did that color already. Panic. I'll do that one. So I have the idea of something like a key value. And it's funny, sometimes you'll look at a key value and it looks like a database. The whole point of key value is there is a key, and then you have some name and a value. So the key could be a hey, ID1, and then its first name equals Clark. Last name equals Kent. So it's just these key value pairs. But if you looked at it, you might organize them and it looks like a table. But every single entity could have completely different key value pairs in there. There's really not any type of strict relationship. So Azure Storage Tables is a good example of that. And there are others, like you might hear, for example, about time series. And the name kind of says, hey, there's something that's really based around time. So there's a time and then there's some data. Maybe it's telemetry coming in, maybe it's logging coming in, but hey, it's all focused around organizing it by that time. Now, if we were to pivot and think about, well, okay, what are some of the types of storage and service we actually have in Azure then around those different services? And realize if we start with unstructured, there's different ways we want to interact with the storage. Typically here it's going to be that unstructured or semi-structured. If it's structured, it's probably going to be in a database service, although there's some exceptions to that. We talked about JSON already. We have that set format around the data. We talked about delimited files, comma, tab, space, where there's some record entity on each line. XML used to be very, very popular. But if it's unstructured or even semi-structured, I just want to store it somewhere. I want some service. And the core one we really think about is an Azure Storage account. So I can have the idea of a storage account. So I think of this blob, for example. So I'm going to have a storage account. Now, out of that storage account, there's many different services that we can actually leverage. Storage account exists in a specific region. I create it, lives within a subscription within a region, but it offers many, many different types of service. And a blob is really the first one. Blob is just, hey, a bunch of ones and zeros. Now, there are different types of blob. A very common one I can think about is block. A block blob. It's just made up of a sequence of blocks. I can have up to 50,000 blocks. The blocks can be variable size that go into that block blob, but it gives me this massive, I think it's like 190 tebibytes is the maximum file size. I can have things like a page blob. A page blob is very good for random read-write access. They're 512 byte pages. Disks in Azure sit on top of page blob behind the scenes. I can fetch single pages at a time, which makes it really powerful for that random interaction. There's append. I can't modify or delete blocks within the file, but I can add to the end of it. So I think logging, it'll be a fantastic for that idea. And then there are services that almost sit on top of that. So for example, with Block, sitting on top of Block is another Azure service, Azure Data Lake Storage Gen 2. And as a data lake, and we're going to talk about this a lot more, that adds things like POSIX style ACLs, a true hierarchy. It has a different API I can interact with. But when I think about all of the different types of files I might want to store in Azure, very, very commonly, I think about Block Blob. I think about that Azure Data Lake Storage Gen 2. So if it's that unstructured data I just want to store somewhere, if I think about that semi-structured, and again, that could be JSON, XML, comma separated values, tab separated values. It could be some of those like database files, that columnar format. For example, there's things like Avro. I mentioned the Parquet already. There's things like Awk. So these are, in a way, they're based around being read from certain types of databases, but it structures that data so I can interact. Very commonly, I'll put those on a data lake. When I think about JSON, XML, and CSV, great, I can read those as a human being. They're not that optimal for machines to read, whereas these things like Avro, Parquet, and Awk, they're really designed for the machines to read and leverage. Now realize there's other types of service I may want. So sure, Blob is one of them, but maybe I want to operate over a file-based protocol. And I want certain services as part of that. So when I think of, so Blob is one service I get from a storage account. I can also have files. And Azure Files lets me have SMB 2.1 and 3 and NFS shares. So now I can go and interact it using those regular standard protocols. So this could be a lift and shift. It could be a hybrid solution. So I'm born in the cloud server. I need some shared storage area that I want to talk to using a file-based protocol. SMB, NFS, I'm used to those. I might even have a scenario where I could think about, hey, in Azure, I create an Azure file share, an SMB file share, but maybe I also still have file shares on premises, running on Windows file servers. So these are all SMB. And what I can do is I can synchronize with that cloud-based endpoint, that cloud file share. I can do tiering. Hey, data I'm not using, just store it in the Azure file share. So this solution is called Azure File Sync. So I create a sync group containing my on-prem Windows-based file servers, SMB, a single Azure file share, and it will synchronize between them, all via this share. Hey, data that's not used a lot, don't store it on here, just store it on here, but pull it down if someone tries to access it on demand. So I'm going to optimize the space I need to use. There's also tables. So I mentioned key value. There's also a table service. So we have blob, files, table, which is key value. And there's also queue. So I think of queue as this idea of how I have a message. I want to write the message to the queue, and then something pulls out. Now, so we say first in, first out. It's not a guaranteed first in, first out. It typically will be, but there could be exceptions. If I need a guaranteed first in, first out service, and there's things like service bus queues that have message sessions to actually guarantee that. Now, if I think about resiliency for my data, and I think about this storage account, from a resiliency perspective, there's always a minimum of 3 copies of my data. Now, what is different is, well, how is that data actually stored? I have different resiliency options for my storage account. So if we think about a region for a second, we always think about a region as that 2 millisecond latency envelope. So if I have one region, my primary region for my storage account. And actually one of the things that gets exposed is you see the idea of availability zones. Availability zones are groups of data centers that have independent power, cooling, and communications. So I might have, and those idea of AZs is going to come up again and again and again. Each subscription will see 3 availability zones. So it could be like an AZ1, AZ2, and an AZ3. Many regions also have a paired region. Now, not all do. Some of the newer regions, like Central Qatar, does not have a paired region, but that also might have multiple AZs, or in this case, just a list set of data centers. So one of the things that's happening here is I have different redundancy options for my data. Sometimes you forget how to spell very simple words when you're trying to draw it on a board and say it at the same time. So different redundancy options. So there's LRS. So let's start with colors. So there's LRS, locally redundant storage. So 3 in a particular data center. So LRS, my 3 copies of my data would be kind of scattered in a certain data center. Then there's ZRS. So there's still 3 copies, but they're over the 3 AZs. So now my 3 copies are here, here, and here. Well, then I have GRS, globally redundant storage. So I have 3 in a data center, and then asynchronously, another 3 in a paired data center, a data center in the paired region. So I might have the 3 here, and then it's asynchronous. It's always asynchronous. Whenever there's a big distance, it's asynchronous, or the performance would be terrible. If there's hundreds of miles, I can't synchronously replicate. So synchronous means before I send the commit back to the app making the write, I make sure it's been committed to the disk in the pair. Well, if there's hundreds of miles, that would be tens and tens of milliseconds of latency, which doesn't seem a lot, but to a computer that's doing transactions, that's huge. So it's asynchronous. We send it as quick as we can, but we commit back to that asking app as soon as we commit it to our primary. And then as we can, we then send 3 copies to that paired region. So we do synchronous within the region. Hey, these are close together. Then there's combinations. So then we have things like GZRS. So there's 3 over the AZs, and then the 3 in the paired region. So now I have my 3 copies spread over here, but then the 3 in the other are not over AZs. In the paired region, they're just in one set of data centers. For some of the services, in this pair, there's like an RA option, read access -GRS, read access -GZRS. So what the RA option, this is optional, it lets me get read access if it's a blob, a queue, or a table. It doesn't work for files. So that's kind of an important point. So it blob, queue, table can get read access. Can't write to it. There's only one primary, but I could read on that paired region. So if I had certain maybe analysis I wanted to do, I had a certain app design where it was mostly reads. So hey, I could read from the pair. That could be a good pattern to use. There's also performance differences available. Now, when I think about my performance, for Azure storage accounts, there's actually 2 types of account. So firstly, I have the idea of a premium storage account. So that's It's just Premium. I have Premium block blob, page blob, files for a higher performance, a lower latency. And then I have the idea of just a standard storage account. But within the standard, I have tiers. I have the idea of a hot tier. I have the idea of a, not exact color. I have the idea of a cool tier. And then I have the idea of an archive tier. And as you can really imagine, the important thing is the archive is offline. If I move something to archive, I can't directly read it. I have to move it back into hot or cool before I can actually read it. This is the most expensive for the storage. So Premium costs the most, then hot, then cool, then archive. But transaction costs are the opposite. Very, very low to sometimes it's free on the transaction cost. Transaction costs go up and up as I move down. So I pay more for the capacity, but less for the interactions with it. So that's one of the key points around it. So if I think dollars for the capacity, either the cost of the amount of data I'm storing, it goes up. But transaction costs go down. So the higher up, the arrow is confusing. So it gets more expensive as I go up, but the transaction costs go down as I move up through them. And we can see that. So if we quickly jump over and look at the pricing for a second. So here, if I look at the storage pricing, what I can see is, well, hey, look, if I look at firstly the capacity, so I can see for Premium, hey, it's 15 cents per gigabyte. And then for hot, hey, it's 1.8 cents per gigabyte. Then it's just 1 cent for cool. And then for archive, it's tiny part of a cent. So I pay less for the capacity, but then for the transactions, the operations, Premium is cheaper than hot. Hot is, so we can see here, Premium. And then if we compare that to hot, so Premium is quite a lot cheaper than hot, which is cheaper than cool, which is, if you look at the read operations, archive is way higher because it has to rehydrate and actually bring that back into cool or hot. Attributes around those services. I get lower latency as well with Premium, the great benefit, but I pay more for the storage, I pay less for the interactions. That's one of the key points. Now within this standard storage account, one of the useful things I can actually do is lifecycle management. So I can enable lifecycle management. What that lets me do is, hey, look, if a file has not been modified or accessed for 30 days, let's move it to cool. If it's then not been accessed or modified for 90 days, hey, let's move it to archive. Hey, it's not been accessed for 7 years, let's just delete it. So it helps me maintain all of that data. Now, when I think about these tiers, it's only block blob, not append or page. So there's limitations on where I can use these tiers. Archives are really useful where I just have some huge amount of data I just need to store, but I don't need immediate access. I could wait hours when I make that request for it to be brought back into the other ones. So that's really the key point around those. Okay, so that's unstructured or typical semi-structured storage accounts are a great feature there. And again, the thing we're really focused on a lot is this idea of a data lake, this ADLS Gen 2, which sits on top of Block, but it's still part of an overall storage account. So that is Pivot. So we talked about, hey, that unstructured and the semi-structured in a data lake in a storage account. What about our structured options? What are the offerings there? These are the more advanced data types we'll actually go and interact with. Now, when I think about database, there's actually two key types. So if I think about my database types, because we interact with databases for different purposes, I can think about, I have my line of business application. So what I actually want is to do transactional processing. Someone's buying something. Hey, I need to log that order. So I can think of OLTP. So this is all about this online transactional processing. So very commonly, for example, my line of business app is going to interact with an OLTP type database. So what characterizes this is I can think about a higher volume, so lots and lots of transactions, but they're pretty small. So a high volume of small transactions. I want fast access when I'm querying, when I'm doing some update or read. So I want very, very fast access. This database is going to be normalized. Remember, the whole point here is I'm removing the deduplication is a very small part of it, but I'm separating out the data into tables specific for the type of entity, and I'm going to reference things between it. So I'm going to normalize my data. So it's split into small, very well-defined tables. There's a huge, huge focus on this idea of ACID. So atomic. Every transaction is a single unit, which either completely succeeds or fails. For example, if someone's buying something, well, there's putting in the order, then there's maybe subtracting from their balance the cost of that new order. And they're two different parts of the transaction. I can't have one succeed and the other fail. They both need to succeed or they both have to fail. I think about consistency, keeping the database in a valid state. Isolation, transactions, if they're happening concurrently, aren't going to interfere with each other. Hey, someone's buying two things at the same time. Durability, if I commit a transaction, it will remain committed even if there's some interruption. Once I tell the app this is committed, it's committed. There are safeguards in place, be it logging or other features, that make sure once the app has been told by the database this is committed, it stays committed. So this is what I'm using with my line of business app. But there's other types of things we need to do. I want to run analytics. I want to run reporting. So then we have the idea of an OLAP, an online analytical processing database. So this is typically a large data volume. So lots and lots of data. My interactions are typically looking at historical data. It's mainly read. Now, obviously, there's some write going in to get the data into there, but it's mainly read only. I think of an example like a data warehouse. Now, what's interesting is, obviously, this is different because my focus here is about, hey, I want to be able to do this analysis. One of the things we might see in a data warehouse is we denormalize the data because I care about the performance of running these big analytical queries against it, because fundamentally my goal for this is analytics. So sometimes we will combine tables back together. We may introduce duplication of data because it will make the analytics we want to run against it that much more efficient. So we care about different things. I want to capture raw data for insights. When I think of a data warehouse, I have to get the data ingested, maybe transformed into it. We'll hear about things like data lakes and data warehouses commonly together. Now, when I think of these services, well, if I think about an OLTP, we think about SQL Server. I might think about Postgres. I think about MySQL. I think about things like MariaDB. From the data warehouse, I think about things like Synapse. So there's different solutions depending on what we're really trying to do. Now, before I go any further, there's different people that interact with the data that we're talking about here. So let's just for a quick second think about, well, who are the actors involved in all of this? So who is doing the stuff against this? So an obvious one is the database admin. And this is really the first person we often think about. So I have the idea of the database admin, the DBA. So I can think about the DBA is responsible really for the design, the implementation, and the maintenance of the database. They're looking at it, they're tuning at it, they create the tables, they say, hey, a new index is probably a good idea to add here. They're doing updates to the database, minor and major updates. They're looking after the database. They have all the operational, the maintenance responsibilities. Now, they don't work in isolation. The database admins are experts in databases. They'll work with the app teams to understand the app requirements so they can correctly design the database, the schemas, the tables, the relationships between them. What's the performance requirements? What's the HA, the high availability? What's the disaster recovery? Have to fail over somewhere else? What's the security? All of those things, they will understand the requirements from the app teams to design the database. So that's their goal. But then we have things like, well, what exactly is the data workload? Because the database is one part of maybe a flow of the data. Someone has to understand what is that flow of data. So then we have the idea of a data engineer. So their goal is to understand the data workload. So they have to understand, where's the data coming from? How is it emitted? How can I read it in? Where do I need to store it? What do I need to do to it? Do I need to transform it? What are the types of interactions required to it? Where do I need it to actually get stored? So I think about this idea of a pipeline that's going to actually bring the data in, maybe store it, maybe modify it, transform it, and then store it in places. So the data engineers, they're going to work all of that out. How do we ingest it? What do we do with it? Where do we put it? Do I have to clean it? All of those things, what are the network considerations? What are the security considerations? They're going to design this. So they are going to design the data pipeline. How do I get it? What do I do to it? Where do I put it? Data engineers are going to enable that by understanding the data workload. And then once we have the data somewhere, generally we don't care about data, we care about what insights, what can we learn from the data. So someone has to work out, well, what are the relationships between the data? Someone has to create models to actually let us do analysis on the data. So then we have the data analyst. So these do things like explore the data. They will go and look at the data. They will find relationships in the data. They will build models. So they'll build models that then the business can use to get insight. So they're going to expose insight from the data. So there are these three key roles that light up data. Someone has to maintain the databases and design the databases, especially for those online, the transactional processing, the line of business apps. Someone else, when I think about the complete lineage of the data, getting it from somewhere, doing something to it, making it usable to then store in other places. Hey, the data engineer has to design those pipelines. And then once we have data in places, how do I get useful insight that might change the behavior of my organization? Well, those are the data analysts. We have all these different roles to make sure everything we get is useful and get the most out of our data. So it really is the key point about all of those different things we're actually going to do. Now let's go back now and start drilling into some of the specific types of service for a second. And I've referenced this already. So we had this idea of a table. If I think about a relational database, SQL, Postgres, MySQL, MariaDB, I talked about this idea of a primary key, which uniquely identifies a particular entity. No two rows can have the same key. So, hey, ID1, ID2, again, could be the employee ID, for example. But one of the useful things about normalized data is I want relationships between them. So we have this idea of, hey, there could be another table over here, which has its own schema, remember. It has its own entities, which have their own attributes, and it has its own key. Imagine this was Office. These were offices, remember. So one of the things I might very commonly do is over here, this might actually reference, maybe it was the office they work at, a foreign key. So it's referencing a key in another table. So it could be like Office 1, Office 1, Office 1. There's a one record called Office 1, and it's referencing those. So this idea of a very strict schema that defines those. And we can look. So if we jump over here for a second. So if I go and open up, close those down quick. So let's go and look at one of our databases. And what we can see is through the query editor. So I'm going to actually authenticate using Azure AD. And now I can go and look at the various tables I have. But if I was to go and look, for example, at the roster, I can see the schema. So I have 4 attributes. Oops. So I have 4 attributes defined. First name, last name, code name, mother name. I was lazy. They're all varchar. But this is the strict schema for this particular table. So that's the data I can have. And then there's the schema of a different table, just an item and owner. Then I can go and look at the data. So here I'm just, again, using this nice web interface, but I'm selecting the top 1,000 entries. And I can see those values. So it's adhering to the schema. Bruce, Wayne, Clark Kent, Diana, Barry. And if the mother name looks weird, it's because it's always encrypted. It's encrypted at the client side. It's using a deterministic encryption, so the same source string will always end up with the same encrypted value. So both Bruce and Clark's mothers are Martha, so the encrypted value you get out of the algorithm would be the same. This is better than using the random in terms of indexing and ability to do server-side operations, but it's not as strong as random for the encryption. But this shows, hey, we have the tables, we have them here in the database, and I can just interact in different ways with them. So let's actually think about this for a second. So we have the SQL, ways to interact, this Transact SQL, which has got some sort of enhancements on top of that. But there are different languages we use when we interact with the databases, and the DBAs, the database administrators, will commonly leverage these. But other people might use subsets of it when they actually want to go and view data or modify the data. So there are different ways to interact. So if we think about the languages for a second, there's an idea of, let's go down here, a data definition language. So the DDL. So the data definition language is all about things like, hey, I want to create, I want to alter, I want to drop, I want to rename, and I'm doing that on tables. Maybe I'm doing it on, I'm creating a stored procedure. A stored procedure is a set of operations that I can then just execute whenever I want. It simplifies having to type them all in. I could pass parameters, but stored procedures let me do that. Maybe it's views. A view is, as the name suggests, I can run a select statement against one or more tables, specify particular columns I want to show, so it gives me a unique view, but it's not storing the data again. It's just a way to see data in a different set of attributes and combinations than how it's actually stored in the database. So the DBA admins will use these to create the tables, alter them, drop, etc. Then there's also the data, I'm not going to type it all out again, control language, the DCL. So this is about permissions. So I'm granting a permission. I'm denying a permission. I'm revoking a permission I gave you already. So this is all about modifying the permissions. Again, the database administrator would be doing this. And then I might think about the data manipulation language. So now I'm interacting with the table and I'm doing things to that. I'm inserting new rows. I'm updating a row. I'm deleting a row. And a subset of this is actually the data query language, which is how I'm doing a select. And there's many other things I can do here. But when I think about the structures of what these are all doing, hey, maybe it's an insert into a certain table name. Just give you an example. And then I tell it, hey, I'm inserting into this column and this column. So I'm doing the names there. And then I'll tell it the values. Clark, etc. I might say select from a certain table. And then I can have conditions. Hey, where, blah, 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 blah. I could order things. This actually might be useful just to go and see this quick. So here in this example right here. So here, what I actually did was this select top 1000 from Justice, which is the group, and then roster, which was the table. But I could take out the top 1000 and just say, give me everything. So just run all the records. So there's the same records that we have right there. But maybe I want to change how it's presented to me, how it's ordering. So I can add different things to this. So for example, I might say, hey, order by last name. And now you can see it's ordered the records. Now Alan is first, then Kent, Prince, and Wayne. Now I could also think about, well, I have data in other tables. So in assets, I have items based on the owner. And realize that owner matches the code name from the roster table. So that could be what I could join on, where that owner equals code name. So that would be a way I could have a join between assets and roster. Almost, I could think of it as that foreign key. So now what we'll do is, we'll do a new query. And I'm going to say, hey, look, select. Now, R is just a reference here to the roster table, which we're going to say. So from the roster, I want last name. From my assets, I want item. So I'm going to get this from the roster table. So here, if I just start typing it, I'll fill out that full name. So from roster as, now I shouldn't have push tab there, so I just want that as R. So R, remember, is going to be the symbol for roster. And I'm going to join it with my assets table. And I want to do that as A. So again, those letters just are the representations of the full table. And then I'm joining it on, well, the roster code name needs to equal the assets owner. So that's how they know they match. So sure enough, now it's, hey, last name and the item. So I did a join on those two different tables. So really just showing how I can do that through just very, very simple things within the language. And once again, that's all this is. R just means the roster and A just means the assets table. That's all these are doing within this query. It's not saying it needs to know in detail, but this is just very much that basic structure. And then, hey, what am I actually joining them on? Quite taxing if I had a lot of data to have to go and look at every single row. So one of the things you will very often do is you add those indexes. We create the indexes and we can add additional indexes. It doesn't have to just be the key. I can add indexes on things that maybe, hey, I manipulate a lot to improve the overall performance of the system. I talked about views already, which are just virtual tables based on some select statement. It's not storing it again. It just gives me a way to interact. And then those store procedures, hey, I have just a set of commands I might want to run periodically. Then I can just exec it. I can pass parameters. I have a lot of flexibility for that. I mentioned over here some examples of the different database types. So one of the things you are going to want to know is some additional detail on the offerings, because even within something like SQL, there's actually different SKUs, different sets of capabilities based on those. So it's important to have a pretty good idea, of what those options are. So we start with Azure SQL Database. So if I think of my Azure SQL database. Now the key thing here, this is fully managed. Oops. I say, hey, I want a new Azure SQL database. Make it so. Now there are different SKUs available to me for this, different service tiers. I can think about there's a general purpose. So I have a general purpose, also standard. And the reason there's two names is there's actually different ways to purchase and bundle in the different compute and storage and I/O capabilities of the databases. There's like a blended model called DTU, but then I can also buy it by vCores and have the storage separate, and we'll talk about that. Then there's also business critical. Also called premium. And then there's hyperscale. And as you can really imagine, general purpose, I have a database server. There's a database server offering my database. The storage is separate. So the data and logs, what happens is if this fails, another instance takes over my data and logs and starts offering my database again. With the business critical premium, I actually have like an always on ring of servers that replicate to different copies of the data and log. So if one fails, another can quickly spin up much, much quicker. So there's multiple database engines. Obviously, I pay more. There are zone redundant offerings where it can spread those, either the takeover ones, the gateways that give me the initial entry into this, and spread over different availability zones. So again, that resiliency from any particular set of data center failures. Within these, there's actually the idea of a single database. So when I create it and give it the resources, just one database gets all of the resource. Or I can do something called an elastic pool. So here I can create multiple databases within that Elastic pool that share the resource. Where that would be useful is if I have maybe databases busy at different times. And so, hey, when one database is busy, it can use more of the resource in the pool. And then when it's quieter, the other one maybe needs more resource. So if I can balance very well multiple databases that need maybe peaks at different times, that can be a really, really useful option to do. And there's even a serverless offering. So that's only for the general purpose on the vCore, but then that just auto scales based on any particular load. So there's also just for general purpose, a serverless offering available to me. Hyperscale is designed for massive performance and massive capacity. It uses separate page servers and multiple page servers to actually interact with the data stored. And then I have this idea of a primary compute node that takes in the requests, and then it distributes that over the page servers to gather the results, aggregates it together, and then passes it back to the requesters. So there are many different offerings based on exactly what my requirements are. And when I talked about those different offerings, if we quickly look at this site, it understands the structure. So here I can see that standard general purpose, that there's a control ring for the initial entry point that the app talks to, and then I just have a primary replica, which then separates out its data and log files. And if that primary failed, well, there were just spares that could then go and connect to the data and log files and offer my service. But it has to recognize, hey, there's a failure, and then fail over. Compare that to the business critical. Well, here, there are multiple of them. So I can see now, well, there's a primary replica, and then I have secondary replicas. Each of them have their own data and logs. And because it's in an always-on availability group, if there is a failure, it's going to pick up that quickly. And just like general purpose, I could separate those over availability zones. And that's super different from hyperscale. With hyperscale, hey, there's these completely separate page servers with a portion of the data that serves it up when I do those queries to the primary. And we can see the options. If I try and create a database, well, if I do configure, right now the default is general purpose, and it's using a combined just vCores and then the data. So with the vCore, I have general purpose, hyperscale, business, and then I have the DTU options. So I can separate those things out. I could change the vCores, I can change the data, I could change the configuration of the hardware, and I have that serverless option because it's general purpose. If I pick anything else, hey, I don't have that serverless offering anymore. On the DTU side, again, that's really the older, that's that more blended set of performance based around the I/O and the compute and the storage. And there are different sort of SKUs available for that. But most people now will use the vCore. I can specify the exact hardware configurations, the number of cores I want. I have a lot of flexibility actually on what I want to do. Now, one other element is, well, we have these SQL databases, but they are just database instances. What about networking? What about auditing? What about logins? And so what happens is these databases do actually sit under a logical server. It's not a real physical thing that really physically has the databases, but it's that server that actually has the other attributes. So if we was to go and look at the server instead of just the database, so notice database is missing some of those other configuration items, but the server itself, if we go and select on this, now I see different options. Now I can see things around the networking, around some of the security elements, around some of the identity, around the auditing. So from a structure perspective, hey, I have this Azure SQL database, but overriding all of these from a logical perspective, they do live under a logical database server. And it's a database server where I can configure, hey, network rules. I can configure things like the firewall. I can configure the auditing, the logins, and all of those various things. Now, something that's going to appear in a lot of these different services, and I guess I should mention it now, and I alluded to it earlier on, but when I think about Azure SQL Database, by default, it's a public endpoint. Now I can use the firewall to lock it down, but it's a public endpoint. If I don't want that, this is where private endpoint comes in. Now, some services integrate into your virtual network, SQL MI, which we're about to talk about. But if you have the idea of, hey, I have my Azure SQL database, and by default, it is a public endpoint. And I don't like the idea of locking that down. I don't trust it. There are things I can do with service endpoints to make certain subnets known and only allow it from a certain subnet within a certain VNet. So service endpoints would let me do that. But again, I can create a private endpoint which points to a particular instance of, hey, this is SQL 01. And if I wanted to, I could then disable the public endpoint. And with a private endpoint, any network that's connected to it can use it as well. I need that DNS. So there's going to be a special DNS name, a private link DNS name that I have to be able to resolve. But then any network could be on-prem or other VNets could now go via this private endpoint. A service endpoint, which I enable for all of the Azure SQL service on a particular subnet, that only works for things in the subnet. So private endpoint is very, very powerful to change and let me do that. So just from a networking, private endpoints are really king. We see those more and more these days. Okay, so that's Azure SQL Database. That's one of the SQL offerings that we see. The other very big one is this idea of Azure SQL. I'm trying to get my spacing right. There you go. MI. So managed instance. The huge point here about Azure SQL MI is it's near 100% compatible if you were just running SQL Server in your own OS. There are many different aspects to SQL. There's like agent jobs, there's different capabilities. Well, in Azure SQL Database, some of those things are not available to you. It's this multi-tenant service. It's very controlled. I can't do everything I could do on a regular SQL server. There's tables that go through the differences. Azure SQL MI, it deploys into your VNet. So I don't need a private endpoint because its target is an IP in my VNet. But it's yours. It's still managed for you. So it's still fully managed and updated, but it lives in your VNet and it has a much higher compatibility with regular SQL. Now, one of the things I can do with Azure SQL MI is I can also, via Azure Arc. So Azure Arc brings certain Azure control plane operations to on-premises, for server operating systems, for Kubernetes. And once it's managing Kubernetes, it can bring certain data services down on top of that as containers, as pods on that managed Kubernetes. One of them is SQL MI. Postgres Hyperscale is another one. So it can actually bring Azure data services to your Kubernetes environment, be it on-prem or even another cloud. So I have Azure, if I need, hey, I need near 100% compat with my on-prem SQL server, Azure SQL MI is probably going to be the solution to do that. It's still automatically managed and maintained. It's just better compatibility. I can have multiple databases in a single Azure SQL MI. Now, the other option is, well, I can have SQL in an IaaS, infrastructure as a service, i.e. an Azure VM. I can just install SQL in a VM. But even then, there's benefits. There's an agent, and it can run in a lightweight mode, or it can run full. And this actually brings management capabilities, even though it's just a regular SQL in an IaaS VM. So here we can see the different features, and we can see, well, depending on the feature, so portal management, hey, I get with lightweight and full. Automated backup, well, it's full only. Automated patching, full only. Key Vault integration, full only. But hey, some of the licensing, some of the flexible version changes, I get with the lightweight as well. And you can go through and you can see, hey, where I do and don't get the feature. And again, this is all about, am I lightweight or full mode? Really, lightweight is the extension is available. Let me just try and find the part in the document that goes through the difference between it. But in lightweight, I have the extension, but it doesn't enable the agent, the full agent inside the operating system. Whereas when I have the full mode, that full agent is deployed and running inside the operating system. Oh, here we go, management mode. So lightweight, hey, we've got the extension, but it does not install the agent. And then the full mode, we actually install the full agent to give the full functionality. Have those different options available to us. So I can install SQL actually just in an IaaS VM, and I still get benefits from that. Now, obviously, when I think about in a VM, I can just install anything in a VM. As long as it's supported by the database vendor, I could put Oracle in a virtual machine, for example, in IaaS. If I needed an Oracle database, well, I could just install it in an IaaS database. But then there obviously are many other types of database available. And you're not on your own. I don't have to just use them in an IaaS virtual machine. There are a whole set of Azure database for. So there are different offerings. So one of them is Azure Database for Postgres. So one of the nice things about the Postgres is it has a fantastic compatibility with Oracle. There's like a 90% compat between sort of the SQL, between Oracle and Postgres. It's built on the Community Edition, which is something in common you're going to see for all of these Azure databases for. But again, great compat with Oracle. There are different offerings for Postgres because it has evolved. They're changing the way they do this. Now, all of them is automating the patching, the backups, but we have this idea of single server. This was the original offering. This was based around their own special containerization technology. It gave you a great SLA. It was 99.99% SLA, even though it's a single instance, because if it failed, it could switch over super quickly to another instance that was just sitting around ready. There was always 3 copies of the data. The computer and data were separated. But it didn't support things like availability zones. There were the ability to add read replicas to other regions. What they've now introduced is a flexible. Now this is VM-based. Now that VM basis now gives me more flexibility. I can do things like the burstable VMs, the B series. I can stop and start, so I can optimize my spend. I can optionally have HA, so I can have a standby server so it will automatically fail over to them. I get far more configuration. There's hundreds of attributes I can now change of my database, so I get much better flexibility of my database that I couldn't do with a single server. There's a PG bouncer, so a broker to handle the connections coming in. I can have a custom maintenance window. It does automatic minor updates. There's also hyperscale. So Hyperscale uses the Citus extension. So this is a standard extension for Postgres. Remember I talked about sharding things? So this does that sharding. It splits the data over multiple shards, over multiple servers. And I do this through distributed tables. So I have a distributed table that then shards over the multiple servers. I can have also these ideas of, if I have certain important data, I can have a reference table. That would be on every server. Maybe data I'm commonly looking up, comparing against, I can do that in a reference table. There's actually two tiers of this. There is a basic tier. So the basic is a single server, so it's one node. So here both the coordinator and the worker is just one box. This is designed to get me started if I'm trying to experiment to keep my costs down. And then there's also the standard SKU where I have one coordinator and then 2+ workers, and I can upgrade. So I could start off with basic. I say, okay, I get it, and then switch over to the standard mode if I wanted to. So I have those capabilities. So hey, I want a Postgres database. I can still have async replicas, but this takes away most of the management for me. It's just provided by the system. So that's Postgres, Azure Database for Postgres. There's also Azure Database for MySQL. And once again with MySQL, I have single and flexible. And then there's also MariaDB. So managed database for MariaDB. That is single only. So we have these different offerings. So MySQL is commonly used as part of the LAMP stack. So on that whole Linux, you have Linux, Apache, MySQL, and PHP. Hey, I can get a managed MySQL as part of that. MariaDB is also very good for Oracle compatibility, and again, built on the community editions. Really just like all of those. There are other things. There's, for example, an Azure managed instance for Apache Cassandra. This is an automated deployment, automated scaling into my virtual network as part of your existing Cassandra ring in a hybrid configuration. So we do have these different options available to us. Now, another big offering. So this was all based around, hey, the relational databases. But we also had that idea, if I can find it, we had that semi-structured documents, JSON, XML. All of the databases we've talked about so far were born somewhere else. They were born on-prem, and then we brought them to the cloud. And enhancements are made to make them better in the cloud. When I think about semi-structured, the key service here is Cosmos DB. Cosmos DB was born in the cloud. And what that means, it was actually designed from the start to support multiple regions. And optionally, if I want, to support multi-write. That is very difficult to do in a traditional relational database. If I want to write my application, I want it to be able to have writes at multiple regions. That's really hard to do. Typically, only one of the regions will be writable. I'd have to write my app. Maybe I can read from the async replica, but write to the other one. Well, then where do I read from if I've just updated it? There's a whole set of considerations around it. And why this is so tricky is that distance thing. If there's hundreds of miles between regions, remember that synchronous, yeah? If I want to make a write here, well, if I want to wait for it to be synchronized over here, so make sure no matter where I'm reading from, I get the latest information, I'd have to wait for that synchronization, get the commit acknowledgement back, and then I can tell the app, yes, you're good to go. Now imagine I'm lots of regions all around the world. The performance would be terrible. So I really need this idea of, okay, I need some flexibility. I need different consistency models to say, look, what am I prepared to give up? Because I cannot have everything. Whenever there's a distance involved, I cannot have guaranteed consistency. I'm going to get the same data no matter where I read from without giving up some performance. Because latency is always going to get introduced with performance. We're used to the idea of CAP theory. So CAP was all about the idea of partitioning and availability and consistency. But in the cloud, and when I do have multiple instances, there's this PAC ELC, which builds on that. But it's all about the idea of else. Else, latency or consistency. Which one do I want? I can't have them both. And that's the whole point of Cosmos DB. With Cosmos DB, it lets me pick. It has this whole idea of variable consistency. I pick. And there's really 5 levels. I can have strong all the way down to eventual. And as the name kind of suggests, eventual, well, we'll get there eventually. In the middle, there's a very common idea of session to guarantee within a certain session, everyone sees the same thing if they read. And there's also kind of these midpoints between them. Now, strong guarantees that everyone, no matter where they are, always sees the same data. In which case, multi-write does not make any sense. Because they still have to go to a same copy. It has to sync everywhere. So multi-region write and strong doesn't make any sense. If I want to guarantee everyone sees the same thing, it doesn't make any sense to write in different places. So that goes away. But for all of the others, you get this idea of, well, what is the consistency I actually want? And I have some nice pictures that kind of shows the consistency levels. So here I can see if we scroll down, it uses notes on the piano. So it goes from this stronger consistency to weaker consistency. So if I think of strong consistency, no matter where I read from, I'm always going to see the same data in the same order. So that's that strong consistency. And I can go all the way down to the weakest, which is eventual. I think I scrolled past it. But if I look at the eventual, then depending on which one I look at, I'll see different data in different orders. There's no guaranteed consistency of it. A very common one we use, though, is this idea of this session consistency. And notice we have different sessions that can be shared by different processes. So here, EastUS2 and WestUS2 are sharing session A. They are guaranteed to see the same data at the same time. So maybe this particular processes require that. Whereas a different session, well, that could see completely different data. So that's really the goal, is I'd set the consistency based on what is it my application is expecting. It's written that you can pick. I pick what is that consistency I actually need. And it supports multiple APIs. So I think about different types of data and interactions I want. It supports multiple of those. So if I think multi-API, well, hey, I might want to use a SQL API or MongoDB when I want to interact with documents. Some of that semi-structured JSON, for example. But I can also use Cassandra when I have that more column-based data. I can have table APIs when it's just those key values. And I can use Gremlin API when I want to use graph. Remember when I had those nodes and the edges that were the relationships between them. So all of those are supported when I think about Cosmos DB. Now, one of the interesting things about Cosmos DB is all of the performance and how I pay for it is with these things called request units. and different operations I perform cost me a different amount of request units. Now, one of the challenges is we have this idea of a provisioned mode, where I say, hey, I want this many request units, and I pay for that many request units. The challenge is it's very hard to get that number right. If I make it too low, I'll get throttled because I've run out, and I'll get event codes to say you've run out, you've been throttled. Or I make it too high and I'm wasting money. And so there's also, with provisioned, I can do auto scale. So with auto scale, and this really is the common one, I can set a min and max, and it will modify it based on the number of request units it actually needs to use. Now, the way this works is you pay a little bit more for the auto scale. Let's just look at the pricing quick. If it's not multi-write. So here, if I look at the pricing, the key point here is, so I can look at the standard throughput and I pay a certain amount of money. So based on the request units, but notice here there's multi-region write costs. If I go to auto scale, there's this 1.5 times for single region writes. So if it's single, not multi-region write, I pay that 1.5 times. But multi-region write, it doesn't have it. It's the same cost. No-brainer to use auto scale. You're just always going to do it. There's no downside to doing it. Even provision though, unless I can operate at a 66% or greater efficiency, which is really, really hard to do in the real world, it makes more sense to use auto scale. It's going to be cheaper. So even though there's that 1.5 price factor, it's still cheaper most of the time because it's really hard to get above a 66% utilization of provisioned. Unless you're really, really steady workload and you've done a huge amount of work to estimate that out, it's just super, super hard to really do that in any real way. There is also a serverless option. That has a smaller scale, but I can stop and start it. But there's a maximum amount of data I can have with that. It might be a smaller kind of workload you have. And then I assign this to a database, and within there I can take containers and tables and all of the other things. If we go back, so if I think about the different database services for a second, so we talked about the idea of the OLTP. These are all relational databases, and then we have those semi-structured, the documents. What about the data warehouse side of things? So there is also OLAP services. So I can absolutely think of Azure, Synapse, Analytics. The board is starting to misbehave. It's getting busy. And this actually tightly integrates with things like the Azure Data Lake. So when I think about that ADLS Gen 2, this service integrates very tightly with the Azure Data Lake. But what this thing does is it separates out its compute and its storage. So I can pause. So this could actually be paused, so I stop paying for the compute side. But what this is going to let me do is it incorporates many, many different elements. It brings many different services together that before existed, but were kind of confusing to work out how do I use them, how do I give them permissions to each other. So it brings them all together. It has things like pipelines. So when I think about building that data flow, it has that. It's using the same as Data Factory, which we're going to talk about. It has a SQL-based data warehouse. So remember that large store of just lots and lots of historical data that I would then want to run analytics against. It has Apache Spark for various types of data manipulations. So I can think about data preparation, getting it ready for some other type of storage, cleaning it, mapping it. I can have things like extract, transform, load, extract, load, transform, which we're going to talk about. I can do things like machine learning. I can do all of those directly within the service. I have a data explorer. So Data Explorer lets me actually have a data analytics solution for real-time querying of the log and the telemetry using KQL. And of course, it integrates very tightly with that data lake. And the whole point of the data lake is, hey, if I store data in here, be it a CSV, a Parquet file, a tab separated, a JSON, well, that can actually be read directly from the SQL pools it has to do further analysis on it. So it really is super, super powerful for the other types of interactions I may actually want to do. So before I go any further, let's just talk about some of the basic tools that I may actually leverage in the environment. So if I think of the tooling, those different personas we talked about before, the database administrator, the engineer, the analyst, they will use different sets of tools. So if I focus for a second on the DBA, so that database administrator, remember, they are focused on the database, the tables, the stored procedures, the views. So if I'm SQL focused, we have the SQL Server Management Studio. Now this is Windows only, but this is going to give me the deepest set of management capabilities. So it's very, very deep management of SQL Server. I can think about interacting directly with things like the query store. I can manage things like SQL agent jobs. So this is management of high availability. I can really control and interact with any aspect of SQL Server. But then I can think about, well, there's also the Azure Data Studio. Now the focus here is, well, it doesn't say SQL in there. The focus is on data services in Azure. So this is, instead of being Windows only, well, this is multi-platform. And I can interact here with different types of database. So yes, I could think about SQL, I could think about data warehouses, I could think about Postgres, all via this nice graphical interface. So it's visual, it's multiple types of database, but it's really focused on interactions querying the data. It is really not focused on that deep management aspects of a particular database. Now, it has extensions. So one of the great things I can do with this is I can create dashboards. I can have visualizations in my dashboards. So there's many different aspects to what I can do with the Data Studio. So you might start to see this used by other roles when, hey, I want to make insights available to other groups within my company. Now, if I think about from a business perspective and how they might want to interact with data, we have solutions like Power BI. Now, Power BI is all about getting me insight. It's all about different types of visualization. And there are many aspects to Power BI. I can have dashboards. I can have the various components within that dashboard coming from many different data sources. It could be a data lake. It could be a data warehouse. It could be Excel. It could be other types of files. And if I think about that journey of the data, we talked before about when it has to get ingested from somewhere, maybe there's transformations and it's stored somewhere, and then I want to analyze it. Think of Power BI being at the end of that chain. When I've gone through that data wrangling, I've mapped things, I've put them into different locations. Power BI is at the end of that chain to help different people get insight from the data. Now, there's a Power BI desktop offering that lets me actually create data virtualizations, create data models, create reports, and then I can publish them to the Power BI service, which is a cloud service that could then be consumed by phone applications through web browsers. So there is a web browser interface. It has some very, very limited data modeling and reporting, but it's not the same as the desktop tool. But I can create these models with Power BI through analytical modeling. I can create relationships between different tables from different data sources via its native model capability. And if you think visualizations, I can really do all of those with Power BI, be it a table and text, be it a bar or column, line charts, pie charts, scatter plots, things on maps. Hey, I have a geographical map showing maybe sales by region, for example. And I can combine all of those into a nice interactive report that could have filtering, values specified, all of it just through that Power BI tool. Now, one other thing I want to talk about when I think about, hey, we have data all over the place, is really this service. I'm going to do it in my Galaxy. I normally save the Galaxy pen. And it's Microsoft Purview. Now, this is one of these newer offerings. And Purview is all around, well, the data can be anywhere. So that data could be in Azure data services. It could be in another cloud's data services. It could be in a certain SaaS app. It could be on premises. And it's in place. I don't have to copy it into Purview. I can give Purview line of sight and has to be able to get to it, has a certain credential, but it doesn't have to copy the data. And a huge part of what this lets me do is it discovers. So it does discovery. What data do I have out there over these services? What is the type of data? So then I can add things like, well, I can classify it. Is it PII? Is it about this certain project? Is it HIPAA related? It will go through and in place classify. And then once I classify it, remember, well, I can then apply governance to it. I can put controls around, well, what do I want to happen with that? That helps me manage risk, helps me match compliance requirements I have to actually the reality of the situation. And when I think about classify, it can be as simple as expressions. Hey, you think about, oh, it's a certain number of numerics, then a dash, then a certain number of numerics, a dash, like find a social security number. But it can also have trainable classifiers. And what does that mean? That means, hey, I show it bunches of data, examples of the data, and then through machine learning, it can learn, oh, okay, well, that looks like that other data I was shown before. Okay, I'll classify it as such. And again, once we classify it, then I can apply that governance to it. Now, this includes things like data in Teams, data in SharePoint, data in Exchange, data in OneDrive, data in Azure storage accounts, data in AWS S3 buckets, databases. So it's going to go and discover the data, go and find the sensitive data, apply classifications, and then I can even add controls through things like Purview information protection. I could add watermarks to documents, for example, say, hey, classified. I could encrypt it. I could add access restrictions to it. It's going to also let me have things like data lineage. So when I think about data lineage, well, where has this come from? What has it gone through? Where has it gone? What's the history of this data? I can see that. I can look at the behavior related to the data. Hey, someone's suddenly doing a mass download. That's a little bit suspicious. Well, I could report on that. I might want to block it. So I have a lot of flexibility around finding the data wherever it is, understanding what is the data wherever it is. I may not know. this data is sitting out on some other service. This is going to help me find it. And that's really the key part of all of this. Now, we talk about data, all these different types of data, and we talk about, hey, we ingest it and we do stuff and we put it somewhere else. Well, how do we get it? How do we get this data? So let's start off with the idea that, well, obviously there's different ways I can actually collect the data. So if I think, I'll make sure I've got enough, so I don't want to run out of space. Let's scroll down a bit. So if I think about data, what are some of the common ways I could get data from something? Well, obviously there's batch. Batch is maybe the most familiar to people. The idea is data is collected in a group. I have a collection of records maybe. Maybe it's the last day of data or last hour of data or whatever it is. There's a big group of it. So typically the idea is this will be processed on an interval. So there's going to be some interval-based processing. Every hour we go and fetch the log file. Every hour we go and fetch the sales data. So typically, because it's a batch and it's accumulating and then we grab it, it's going to be a very large volume. So we associate the idea of a large volume of data in the batches. And because we're collecting it and processing it in groups and there's a time between each of those iterations, there's going to be a latency. This is not real time. There's going to be a delay between maybe that data being created and then progressed through whatever this pipeline, this workflow is going to be. And then I do some work on that. That's very different from the idea of streaming. If you look at the model world we're in today, think about Internet of Things. These tiny fridges and sensors, they're connected to the internet, they're constantly emitting telemetry. That time-based, hey, my CPU percentage or my heat or those things, they're constantly streaming actually a lot of data. When you have millions of these things, that's a massive amount of data that's not in batches, it's constantly being sent to some target. So the idea of when we have a streaming is we process as it arrives. Whereas again, with batches, maybe something's writing it and it just sits and writes it to a file that accumulates, or lots of files accumulate, but they just get grabbed in batches and then something happens to them. So because of this, this is real time, or we talk about near real time. It's really, really quick. So this had potentially a high latency. This would be a very, very low to almost zero latency we would think about. Now, because of this, processing it as it arrives, and maybe even it can't send the next bit until we process it, I have to really think about scale. This cannot be a bottleneck. So I need to make sure when I do streaming, whatever is receiving this data has to be able to handle the amount. So again, I talked about the example of Internet of Things. Imagine maybe I'm doing tweet analysis. As soon as people tweeting, I'm grabbing that. Maybe it's stock prices. I'm constantly grabbing as the stock price changes, and I'm doing some analytics. I'm doing things on there. Now, when I think of streaming and I think of services, one of the big ones we have in Azure is Azure Stream Analytics. So this is designed specifically to be that target as you've got these sources of data coming in. So it's real time, it's a managed processing engine. It's going to capture the stream from the input. I can run queries against it. It can extract bits of data from it and then output to other targets for further analysis. So it's doing both the ingestion, the capture, but also the processing in one part. So if I think about, well, where's it coming from? This could absolutely be kind of IoT. There could be IoT Hub. So Azure IoT Hub, for example, it could be coming in from IoT Hub. It could be coming in from blobs. People are writing these blobs. It could be from Event Hub and then other things as well. It's getting them. It could be selecting. It could be aggregating over very, very small time windows potentially. And then, hey, I can send it. I can send it, maybe I'm sending things to a data lake, maybe a data warehouse. Maybe that real-time processing, I'm actually going to generate alerts. Hey, this temperature sensor on this piece of equipment is risen to a certain level. I'm going to alert so we can do safety things, so we can stop things happening. And we can do that because of this very, very low latency, because it's near real time. So that's really the key part around that. Now, this all is great, except the challenge is very often this data is coming from many, many different things. And it's typically not in the format we want it to be. Because maybe I don't have the ability to change the output format, what is generating these, but it's not in a good format for me to actually analyze, to process. Maybe it's not normalized, it's not in a fixed structure, it needs to be cleaned up. There's bad data. I need to clean all that up before I put it somewhere to do analysis against. So I need some set of processes to make this good. Because again, the data can come from many, many places. If I think about all of the different things that could happen to this, remember what we talked about before. I have to ingest it from somewhere. So I have to think about an initial extract. Now again, that extraction could be coming from a device, from a form, from a database. How do I get this in the right kind? It could come from batch, it could come from streaming. There's a huge amount of different sources that I could be having to extract from. But then again, I need to get it into the right format to do work against. So then we think about, well, I have to transform it. And there's different types of transformations, and we'll talk a bit more about that. It could just be cleaning it up. It could be standardizing formats of dates to a certain format. It might be taking out bad data. It might be combining fields. And then once I've transformed it, then I have to load it into whatever system is actually going to go and do the work about it. So we have these extract, transform, load. It's a very popular concept. Hey, we get the data from somewhere, we get it into the format we need to do, transforming structures, removing bad data, standardizing certain attributes, filtering things out. And this really comes from the idea that we transform it before we load and store it, because maybe there was limited amounts of storage. So I want to transform it, get it in the right format, and just store the data we want, that we know we want to run the analysis against. But the problem with extract, transform, load is, well, one, that whole idea that storage is super expensive in the old days doesn't really apply anymore. Like a data lake is super cheap. But also, once we've transformed it and discarded maybe data we don't care about, I can't come back at a later time and say, well, actually, I want to be able to see those other attributes. We can't, we dropped them. And so a very common variation on this is actually now we do an extract, we do a load, and then we do a transform. And then load it into something else. And when I think about this load, the point of what we do here, guess what? We put it in a data lake. So we keep it in its original unmodified form. So we extract it, we store it straight away. So this is this ADLS Gen 2, remember, that sits on Blob and is super, super cheap. So this is loading it in its raw. We're not trimming, we're not filtering, we're just taking it and storing it, which is why commonly seen things like Parquet files, for example. We might just put these in here, or it could be CSVs, it doesn't matter. Then we can transform it and load it. But if in the future we say, do you know what, I need the data, different data, I need it in a different format to do this new type of analysis, I can go back, I can load in new data from that raw and load it in different ways. So extract, load, transform, and then it is going to load it again, actually gives me a lot more flexibility for things that I don't yet know that I need to do. So because I can always go back. I can always go back and load in different data from my data lake to transform it in different ways and then store it. So that's why this is very, very powerful now, that because we have these concepts of very, very cheap long-term retention, let's not discard it. Let's store everything in that original format, because I can always now come back to it and get new types. And again, we have things like tiering on Blob. Hey, that hot, that cool, that archive. I can take advantage of that lifecycle management, so I can really optimize what I want to do. Now, there's even ways that I might be able to directly access the files in the data lake. I don't even have to have something do some new transformation. We'll talk about Polybase, which lets me essentially take files and expose them as tables in some database service. You'll hear concepts like schema on read. So ordinarily what we do is in these transformations, we take the data, we transform it into the fixed format that's got the schema. So it's a schema on write. So we go and we transform it and store it. So it's as we write the data, we've converted it to the end format that's very easy for the analysis to work against. But if the analysis wants to go directly against the data lake, there's a concept of schema on read. It will convert it on the fly to this format to which you can run queries against. It's more expensive in terms of computation, having to apply that. It's going to be slower, but I can do that if it's maybe a more ad hoc type interaction. So that there is that concept of giving me, it's going to be slower because it's having to apply it as it's reading the data. Now, I mentioned these transformations, and again, realize there's different solutions when I think about the transformation. There's very simple types. Mapping. Hey, this field goes over to here. And services like Data Factory can do very, very simple mapping. I could write an Azure function to do very simple mapping. But then there are more complex analytics type transformations. And that's where you'll hear about things like HD Insight and things like Databricks. These can do very complex analysis, interactions with the data. And we'll come back to that in a second. But let's take a step back though. I drew this idea of extract, transform, load, or extract, load, transform, load again. Is this happening by magic? Like, what is doing this? How do I get this whole thing happening? Surely something has to drive this whole process, and absolutely yes, it does. What we need is for all of this, all of these interactions is orchestration. When I think about that data lineage, if it's coming from somewhere, it goes through some process, it gets stored somewhere, something has to drive the things that are happening to the data. So I have to actually think about, there's a control flow actually calling the things that are going to operate on the data, but that control flow itself is not changing the data, it's calling other things. Then there's the data flow itself that will interact and modify. So from an orchestration perspective, we have Azure Data Factory. So the point of Azure Data Factory is source. Where's it coming from? To sync. Where does it end up? That's the goal of Azure Data Factory. And its focus is all about that control plane, the control flow. It is not typically modifying the data. Now, it can do some basic things if you want it to, like that basic mapping capabilities. But its primary goal is focused on calling other things that will do activities that may or may not change the data. I think about the idea of within Data Factory, I create a pipeline. So I create this pipeline that's going to drive calling various things. So it's going to call, hey, activity 1. Maybe activity 1 is write it to a data lake. Then it's going to call another activity. Okay, well now it's been stored in its raw format, Maybe now I'm going to call Databricks to do some analysis on that data. Oh, then it does some other things. And then eventually, hey, I'm going to go and store it to different places. I'm going to go and write it. So Azure Data Factory is the orchestration that gives me that complete flow of the data. It's going to talk to the systems to be able to do the extraction. It's going to call things to do transformations, and it's going to go and put it in different places. And when I think about the interactions, I can have different triggers. So what's going to trigger this? It could be a schedule. Hey, there's a batch. I want to go and grab every hour, grab this data. It could be events. Hey, a blob is written to a storage account, go and grab it. It could be manual. There's many different ways that I can trigger these. And the point is I can have many different sources. Source 1, source 2, source 3. It could be streams coming in. It could be data from a database. It could be logs. All of those things, it doesn't matter, but I'm going to have this complete flow going through with this orchestration. It's doing all of that work for me. So again, focus on Data Factory as the control flow. It's the control plane that makes sure activities get called in the order. If there's logic, hey, I need loops, for example, it's going to do that within here. It can handle hybrid environments. This can be coming from Azure. It could be coming from on-prem. It could be other clouds. It has a nice little UI that I can construct these pipelines. There's an integration runtime that I could run on a system. So if it doesn't have direct access, I can do an integration runtime that can give it access to data just where it is. So there's different ways it can interact. But remember, the key point is, it's typically not doing anything to the data. It's going to call things that will do things to the data. That's the whole point. So if I think about this, remember, this is the workflow. It's going to be the data engineer. This is not a database admin. It's not a data analyst. This is the engineer. The engineer is responsible for understanding all the data and understanding, well, how do I get it? What needs to happen to it to get it in a state? So then the analyst could now go and actually do useful things with it. Now, when I think about some of these common activities, and again, Data Factory can do basic mapping things. But if I think about richer types of interactions to transform and get insight from our data, typically to perform these activities, there's really two key services. A big one is Azure Databricks. Now this is Apache Spark based. So Databricks is an Apache Spark based large-scale data analytics solution. So it's designed to give analytics information about my data. So Azure Databricks is just an automatically deployed and managed Databricks instance. It's using virtual machines. It's using blobs behind the scenes. It can auto-scale. So this is all about Apache Spark based. It's fully managed. It can give me things like auto scale. But if I'm those data engineers and I want to use Databricks in Azure, hey, I'm going to use Azure Databricks. I have the idea of notebooks that I can leverage, which is going to give me the ability to both enable analysis of the data, but also collaborate between different data engineers, between data scientists, between the business users. So this is a very specific service. That is also Azure HD Insight. Now this is all about Azure hosted clusters of Apache open source data processing solutions. There's a whole bunch of these. So they're all Apache something. And so we have Apache Spark. Remember, Databricks was a particular implementation built on top of Apache Spark. So it's this distributed data processing system. It supports lots of different languages and APIs, including things like Java and Scala and Python and SQL. But it's all about doing that data processing. It's distributed, it splits it over so I can accelerate how that's actually processed. Then there's things like Hadoop. So Hadoop, again, is a distributed system, but this is designed to process very, very large volumes of data across multiple clusters. You can create these MapReduce jobs that I can write in different languages, but it can basically now two-phase the data so it can be processed and split more efficiently. There's things like Apache HBase. So this is just an open source system for large-scale NoSQL data storage for querying. There's Kafka. There's Storm. So Kafka is a message broker for data stream processing. Storm is just an open source systems for real-time data processing through these various topologies. And typically the whole point, and I've kind of tried to show this idea here, but a super, super simple example, I can think about, well, hey, I've got data. And again, it might be different sources. I've got data source 1 and data source 2. And I have to firstly ingest the data. So my first step would be, okay, well, we need to get the data in. Well, that would be Data Factory. Azure Data Factory would handle that. Now remember, Azure Data Factory is now involved in all of the steps. But now Azure Data Factory would be thinking about, okay, well, I'm going to load. I'm going to put it in a data lake. So I have my ADLS Gen 2, for example. So I'm loading it. I'm keeping it in its raw format. But then I'm also now going to do a transform. So I want to get it in a fixed format. Maybe I want to actually get some analysis against it. So maybe I'm using Databricks. And again, Data Factory is that control flow, remember. It's doing these various things. And then maybe, okay, from there, I'm going to do a load into Synapse. I want a data warehouse. Synapse, remember. And one of the interesting things is Synapse actually has all of these things kind of built in. So although we talk about Azure Data Factory doing this, Synapse can use Data Factory to light up and enable these types of functionalities for you. And then once it's here, or maybe I've got Power BI, which is going against and doing that analysis against it. But maybe again, this load will sometimes, and the various interactions, I might run queries on here that actually go directly against the data lake using Polybase, which is a way to surface the data from the files directly as these virtual tables within the solution. I can go and interact with it without having to do other things. So that might just be one example of a flow that I may have. So there's lots of these components come together. Now there is another solution that we didn't really talk about, and I guess I should super quickly. If you've used Azure, you've probably seen Log Analytics Workspace. It's a store for all my telemetry, my logs, and I can use the Kusto query language, KQL, to run queries against it. Well, that service actually sits on top of something called Azure Data Explorer. So this is all about log and telemetry ingestion. And then using Kusto query language to say table name and then what I'm looking for. I can write very, very complex queries to get analysis against the data. So if this was like logs, well, maybe I would actually use it directly into Azure Data Explorer. If it was just logs or telemetry, I might want to use Azure Data Explorer, which has got this huge scale capability, but then I can run these great queries directly against it. So depending on exactly what I want to do, Azure Data Explorer may actually be a very good solution for that. Now, I guess one final thing, I talked about Power BI, and I talked about the whole point of Power BI is it's great to actually do that analysis against. realize there are many, many types of analysis. I might think about descriptive. What happened? I might think about diagnostic. Why did it happen? I might think about predictive. Based on history, what will happen? Prescriptive. What should I do? And cognitive. This is all about giving me conclusions. So cognitive, hey, based on existing knowledge you have, give me conclusions based on what this all means. And the whole point about Power BI is it can visualize all of this. I can bring different pieces of data together. I can create models to then make this more digestible to the end business and actually get true insights from the data. So that's what I wanted to cover. So the key point really for the DP900 is, are you going to be an expert in every one of these things? Absolutely not, nor do you need to be. The point is understanding, hey, look, there are these different services available. Understand examples and where I might want to use them. Hey, I just need to store a whole bunch of unstructured data. Oh, well, a data lake would be great for that, and that sits on top of Blob. I need a system where I want multi-write capability with flexible consistency for my born in the cloud application. Oh, that sounds like Cosmos DB. I want a managed SQL deployment in my virtual network that needs full compatibility or near full from my on-premises SQL server. Oh, SQL managed instance. Hey, I'm using the LAMP stack. What service would help me do that in a managed way? Well, LAMP stack, remember, part of that is MySQL. So there's a managed MySQL offering there. So understand what the offerings are. Understand, hey, the different maybe options that are available, the capabilities. I would stress, do not panic. At the end of the day, again, if there's something you don't know, then eliminate the obvious wrong answers. There's always answers that say cheese, and it's not cheese. Get it down to a set you think it could be, and pick the one that seems the most logical to you. Again, things are not named in Azure, they're not structured to make it hard for people to use. They want people to be very intuitive. If you don't pass it the first time, you'll get a score report and it will show you where you was weakest. Just go and focus on those weaker points and you'll get it the next time. So a lot of work goes into creating these. A like and subscribe definitely is appreciated. But I wish you good luck. I'm sure you're going to crush it. And I'll see you on another video.